Okay, good morning, guys. Sorry. So today I want to pick up where we left off last time, talking about sequences. We're going to talk about convergence of sequences, and I'm going to discuss a handful of theorems for sorting out when sequences converge and just kind of trying to get a better feel for what sequences do in general. Turn this on, switch this over. Oh, this isn't connected. All right, come on, come on. There we go. All right. So this. Today is going to be more discussion of sequences. If there's time, we might introduce series a little bit, but otherwise I will be putting together a collection of materials for you guys to kind of leaf through and become accustomed to the ideas of series, because it's a difficult section. Sorry, I'm sure like many of you, me without my coffee at 8 a.m. is a very different character than me with my coffee at 8 a.m. So I'm doing my best to rapidly caffeinate. Let me pop open the textbook to section 11.1 and give you a quick feel for something here. All right. So last time we looked at the definition of a sequence having a limit, and we got used to the notation. We got a little bit of practice finding the limit of a sequence. We even talked about this little result right here. But what you can see here is that there are many theorems in this section. And they take a little bit of practice. In addition to having many theorems, there's also a lot of new notation, and there's a handful of things that are, maybe classifiable as results, but not necessarily theorems. So I encouraged you to read section 11.1 after our last class. And if you haven't done that yet, that's okay. I just want to encourage you once again to read section 11.1. So if I remember right, last time we stopped after defining a recursive sequence. So today I'm going to talk a little bit about some other special kinds of sequences. We learned the renormalization trick. We haven't discussed the squeeze theorem in this setting, so I'm going to pick it up here. Okay. So you'll remember this one, right? If f of x is a continuous function and an is a sequence that is trapped along that continuous function, then the limit of an is the same as the limit of f of x. So this result on sequences being something that you can split up like that shouldn't be too surprising. They're the same as the limit laws you learned in Calc 1. So if an and bn are sequences, then the limit as n goes to infinity of an plus bn is the limit of the an's plus the limit of the bn's. And you can swap the plus for a minus, and the result is still true. Similarly, a limit of a product can be handled by taking the limits separately. Limits of quotients. As long as the bottom piece here isn't 0. There's a few others that we could put in here. I don't know if the book shoehorns them in here or tries to get them as a result on theorems relating sequences to continuous functions. But I'll go ahead and say it, the limit as n goes to infinity of a root or a power. This works fine as well. And 4 is actually a special case of the next theorem. So these rules should look familiar. These are the exact same rules that you learned for limits of continuous functions back in section 2.3 of the textbook in Calc 1. Only instead of having two functions, f of x and g of x, now you have two sequences, an and bn. It's really not worth going through the proof of this theorem because, again, same as the proof for continuous functions. We're just taking the limit as something goes to infinity here instead of the limit as x goes to c. But the result is literally identical to the result on continuous functions. One more theorem. If f of x is continuous, and specifically continuous at L, and the limit as n goes to infinity of an is L, then, and this is pretty cool, the limit as n goes to infinity of f of an is equal to f of the limit as n goes to infinity of an. In other words, it's equal to f of L. So this last guy is really useful. This last guy says you can shove limits into and pull limits out of continuous functions. In some settings, this is taken to be the definition of continuity at L. It's called sequential continuity. And in certain real analysis settings, this is what we take to be the definition of a function being continuous. So I want to show you one or two examples of this. Both of these theorems, they're very similar in their nature. So let's give you a little bit of a feel for why these are useful. It's stuff that probably you would do intuitively, whether I told you you could do it or not. And this is sort of thing that folks just like to do. So let's see if we can calculate the limit as n goes to infinity of an, where an is, say, the square root of n plus 1 over n minus 1 squared. So the thing I'm trying to calculate is lim n to infinity square root n plus 1 over n minus 1 over n squared. So how can I make use of these limit laws? How can I make use of that theorem? Yeah, certainly. I would like to use, I've done my best here to incorporate as many as I could into a single problem. So I claim that I can use the theorem on the bottom, limit law 4, limit law 3, and limit law 1, all in this problem. Really, limit law 3 isn't going to come in play directly here, but the theorem 4 and 1 all will. Good. First, the 1/2 power here. This is the limit as n goes to infinity of n plus 1 over n minus 1 over n squared, all raised to the 1/2 power. And so using the fourth limit law, I can shove this limit inside. And this is also, you could think of this as making use of the theorem, because 4 and this theorem, 4 is really a special case of this theorem. The square root function is a continuous function. So I can shove the limit inside. You can think of it either way. So this is lim n goes to infinity. And then the inside here is n plus 1 over n minus 1 over n squared, close, close to the 1/2. Which one of these laws is natural to apply next? Good. Inside here, I'm trying to take the limit of a difference, right? So according to that first limit law, according to this first limit law, I can now take the limit of each of these pieces separately. So I get paren lim n to infinity n plus 1 over n minus lim n to infinity 1 over n squared, all to the 1/2 power. You see? Yeah, good. Okay, what is the limit as n goes to infinity in n plus 1 over n? Or what trick can we use to sort it out? Okay, so Maggie's correct, but we need to think about why. Yes, the limit is 1. The top, n plus 1, is going to infinity as n goes to infinity, and the bottom is also going to infinity. Now, infinity over infinity is not always 1. I want to be super duper clear about that. Infinity over infinity is an indeterminate form, and I could craft a limit that looks like infinity over infinity to go to whatever real number you want, right? Infinity over infinity is an indeterminate form. It's ambiguous. It could be anything. We can't cancel infinities and get 1. That doesn't work. But there is something else here which does work, and we talked about the something else last time. What did I say the most important trick? Yeah, something like that, right? We can renormalize. And what about this guy? So this piece I'm going to renormalize to get the limit, which is similar to like, yeah, force factoring an n out. What about the second piece here? What does he do? This piece goes to 0. Yeah, this was one of the things that we cooked up last time, right? Remember, n lim n to infinity 1 over n to the p goes to 0 for any positive power p. This was one of the theorems from last time, or one of the results from last time. And this piece I will renormalize. So I'm going to rewrite this as lim n to infinity. If I divide the top by n, I get 1 plus 1 over n. If I divide the bottom by n, I get 1. And then this piece is just 0. So here I've renormalized. And that's a trick you really want to get comfy with. If you wanted to, you could also apply L'Hopital's rule here, but applying L'Hopital's rule is a little bit complicated in the setting of sequences, and if you can avoid it, you really want to. So now that we've renormalized, dividing everything in this expression by n, I have 1 plus something that goes to 0 divided by 1. So this is going to be 1 plus 0 over 1 minus 0 all to the 1/2, which is 1 to the 1/2, or the square root of 1, which is 1. Now here I'm being very verbose, right? Very explicit with every single little step I'm using. In practice, we want to get considerably faster than this. I think what most people would do once they've had a little bit of practice is look at this expression, say, well, I just care about what the inside does, and then I'll take the square root of that. So rather than going through this explicit process of rewriting as a power with the limit inside, we would just ask, what does the inside do? This piece, you can think about renormalizing and see right away that it'll go to 1. Shouldn't be terribly hard. The top largest power here is n. The bottom largest power here is n. The coefficients of both are 1. So when we renormalize, I'll get 1 plus some stuff that goes to 0 divided by 1. And then this piece also, we should be able to see right away goes to 0. So you'd say, okay, I want the limit of this thing. So I'm going to think about what the inside does. This piece clearly goes to 1. This piece clearly goes to 0. So you could jump right away to something like this, and then write down the answer. But I want to show you at least once or twice where all of those intuitive steps come from. Those intuitive steps that admittedly most people can do in their head once they get a little bit of practice, come from these limit laws. All right, let's get a little more practice. How about the inverse tangent of the natural log of 1 over n? Yeah, good. The theorem on continuous functions is relevant here, right? Because the inverse tangent function, that's continuous everywhere. But the natural log function isn't continuous everywhere. So here we're going to have to think a little bit carefully. As n goes to infinity, what does 1 over n do? What does the inside of the natural log function do here? He's going to 0. And in fact, he goes to 0 from the right. Yeah, 1 over n is positive as n goes to infinity. So there's a notation I like for this. As n goes to infinity, 1 over n goes to 0 plus. So this looks like the inverse tangent of the natural log of 0 plus. And by 0 plus, I mean goes to 0 and is positive, or goes to 0 from the right. Okay, what does the natural log function do as its inside goes to 0 from the right? Having recently graded your tests, I have a pretty good feel of how many of us know the graph of the natural log and how many of us don't. This is one of those things that you really can't escape. You must learn the graph of these logarithm functions. So as the inside of the natural log goes to 0 from the right, what does the natural log itself do? Yeah, he's diving down to negative infinity. So the natural log of 1 over n is points along this guy. In other words, the inside here, ln of 0 plus, is going to negative infinity. And what does the inverse tangent function do as his insides go to negative infinity? Good, he goes to negative pi over 2. Excellent. And that again is coming from knowing the graph, right? Knowing the graph of the inverse tangent function. Okay, right, and this of course is the line negative pi over 2. And up here is positive pi over 2. So here's an interesting example where we're using our theorem on continuous functions, but we're also kind of dealing with some weird symbols, the 0 plus and the infinity symbol. Are there any questions about what we did here? Are we all feeling pretty comfy? So as 1 over n goes towards 0, the natural log of 1 over n goes to negative infinity. And as his inside goes to negative infinity, arctangent goes to negative pi over 2. No, I'm afraid the natural log of 1 over n approaches negative infinity. So 1 over n, as n goes to positive infinity, 1 over n goes to 0. And as the inside of the natural log function goes to 0, the natural log function itself approaches negative infinity. That makes sense? And so what we're looking at is the inverse tangent of something that goes to negative infinity. We know that as the inside of the inverse tangent function goes to negative infinity, the whole function, the outside, goes to negative pi over 2. All right. Other questions or comments on this one? So in addition to knowing these limit laws and stuff, it is important that we know the graphs of the relevant continuous functions, especially like these so-called transcendental functions, the functions where you can't like sneak together a graph by plugging in some points. We really just need to know what those look like. That's important. Even here, even talking about sequences. There are a few other theorems that are very useful. This says that the absolute value of a sequence goes to 0 if and only if, that's what this double arrow means, is if and only if the sequence itself goes to 0. One direction of this implication is fairly obvious. The if direction is fairly obvious, that the absolute value of your sequence will go to 0 if the sequence itself goes to 0. That's a consequence of the continuous function theorem. If the limit of an is 0, then of course the limit of the absolute value of an is 0, because you can shove the limit inside the absolute values, and then the absolute value of 0 is 0. But the other direction is a little bit less obvious, that if the absolute value of your sequence goes to 0, then the sequence itself goes to 0. This is especially useful for so-called alternating sequences. We looked at the -1 to the n sequence, and we saw that that is a divergent sequence. That sequence does not have a limit. But what if you divide by n? Well, now the top, the -1 to the n, so here a1 is -1, a2 is +1/2. I'm just plugging in n values here. A3 is -1/3. A4 is +1/4. So the graph of this sequence looks like A1 is -1. A2 is +1/2. A3 is -1/3. A4 is +1/4. A5 would be -1/5. And A6 would be +1/6. From the graph, do we have any sort of guess as to the limit of this sequence? This is the graph of the sequence an equals -1 to the n over n. So as n goes to infinity, as I wander off in this direction, do those dots appear to be approaching any particular y value on this graph? Yeah, this looks like it's going to 0, right? The next dot would be like right here. And the next dot after that would be like right here. These are definitely getting closer and closer and closer to 0. So from our intuitive definition of the limit and the graph, we can at least come up with a guess that this sequence has limit 0. But if you try to just jump in taking limit laws, right, we could say lim n to infinity -1 to the n over n. You could try taking the limit of the top and the bottom separately, and you can always try that. But here, remember the top on its own, that's a sequence we played with last time. That doesn't exist. And the limit of the bottom on its own is infinity. And so this is frankly just confusing, right? I don't know, can't tell. I have no idea what that means. Does not exist over infinity. From the graph, again, we think it's 0. So what we need is some sort of tool that lets me get in there and actually work with this thing. And that tool is precisely the theorem above. So I think that the limit is 0, but my problem is this top is a DNE. So my theorem tells me that, okay, well, if you think that the limit of your sequence is 0, that will be true if and only if the limit of the absolute value sequence is 0. So why not play with the absolute value sequence instead? This only works for 0, so you only do this to sequences you think are going to 0, but you're having a hard time calculating the limit of. Now, I don't know how comfy you guys are with rules for absolute value, but absolute values are multiplicative, meaning they play nice with multiplication and division. So this is the same as lim n to infinity, absolute value of -1 to the n over the absolute value of n. So you can split absolute values up over division and multiplication. Also, absolute values commute with powers, meaning the absolute value of anything to the n is the same as that thing in absolute value to the n. So the top can be rewritten like this. The nth power can pop out. And the bottom, n here is positive. I'm sending n to infinity, so all of the n values I'm interested in are positive. Remember, with our sequences, n is never negative. We only ever consider inputs for sequences like 0, 1, 2, 3, 4, 5. So none of those are negative. So the absolute value of n downstairs is just n. I want to take a second and make sure you're comfy so far. So I'll say it one more time. Absolute values play nice with multiplication and division, meaning here I have the absolute value of some fraction. That's the same as the absolute value of the top divided by the absolute value of the bottom. You can split up the absolute value over the fraction. And then to go from here to here, I'm using the fact that absolute values play nice with powers. Where's my little note? The rules that I'm using here are the absolute value of x over y is the same as the absolute value of x over the absolute value of y. And the other rule I'm using here is that the absolute value of x to the y is the same as the absolute value of x all raised to the y like this. Two important rules for absolute values. While I'm writing down rules for absolute values, another one that we're going to use a lot is that the absolute value of x times y is the absolute value of x times the absolute value of y. So these are kind of three basic rules for absolute values. So I use the first rule to go from here to here. I use the second rule to go from here to here. What is the absolute value of -1? Good, yeah. This piece right here is 1. So this is the same as the limit as n goes to infinity of 1 to the n over n. What is 1 to the n? No matter what power I raise the number 1 to, I'll always get 1. So this is the limit as n goes to infinity of 1 over n. Oh shit, I know that guy, that's 0. So this is how you prove that this sequence that we're playing with here converges to 0. You use our theorem on absolute values of sequences. Zoom out so you can see the theorem at the top. I need to write something in order to finish this up, because I haven't actually computed the limit of the ANs. The limit of my sequence is still right here. But what I've shown down here is that the limit of the absolute value of my sequence is 0. So I would wrap this up by saying, since we've shown that the limit as n goes to infinity of the absolute value of -1 to the n over n is 0, it follows from our theorem that lim n to infinity -1 to the n over n equals 0 also. Is everybody understanding the logic there? All right, so what this theorem says is that any sequence going to 0 has absolute value going to 0. And if the absolute value goes to 0, then your sequence goes to 0 as well. So you could use it in either direction. But the useful direction is always, if the absolute value goes to 0, then you go to 0. So here we were able to show that the absolute value of our sequence goes to 0. Hence, we can conclude from our theorem that our sequence itself must go to 0. Another way to handle this particular problem is through what's called the squeeze theorem. And you may remember the squeeze theorem from Calc 1. Last call for questions on this guy. Okay. So I think this is going to be our final, or one of our final theorems, the last theorem that we'll use often. In France, when they teach this, they call it the policeman theorem. It says if AN is less than BN is less than CN, these are all sequences, and the limit of the outer sequences, AN and CN, are both equal to L, then the limit of the middle guy, BN, is equal to L also. So I really like the policeman characterization here. It says if there's a policeman behind you and a policeman in front of you, and they are both going to the police station, then your ass is also going to the police station. All right, like you imagine you're walking, there's a cop behind you, a cop in front of you, and they're both going to the police station. You are also going to the police station. That's the joke. Or the alternate characterization of the theorem from the French. So we could have used this on our last problem. The observation here is that -1 to the n is always between -1 and +1. It's never strictly in between, it's either -1 or +1, but it's true that -1 to the n is always less than or equal to 1 and always greater than or equal to -1, which means -1 to the n over n is always trapped between these guys. So I would begin by saying, observe that -1 to the n is always bigger than -1 over n and always smaller than +1 over n. This is a fact from algebra, right? That -1 to the n is always between -1 and +1. And then you can divide through an inequality by positive terms without changing the inequality. Also, the limit as n goes to infinity of -1 over n is 0, and so is the limit as n goes to infinity of +1 over n. Thus, by the squeeze theorem, the limit as n goes to infinity of -1 over n to the n must be 0, also. So I'm hoping that you guys remember what the squeeze theorem is and how to use it more or less from Calc 1. You have to build an inequality with your guy in the middle. And then if the two outer guys have identical limits, here both of the outer guys go to 0, then the inner guy has to have that same limit as well. Did anybody not see the squeeze theorem in Calc 1? Anybody's Calc 1 teacher not cover that? Okay. So then the last thing I want to show you today is another one of those very important results. So what we've been doing so far today, this is fun, right? We have some theorems, we can play around with some sequences. You remember last time I said the renormalization trick is the single most important result on sequences. I want you to remember that. The renormalization trick is the most important result for taking limits of sequences. There's one other thing that is kind of at the same level of importance as the renormalization trick, and it's none of the shit we've talked about yet today. All of this is kind of fun stuff. The other major result is the result on geometric sequences. If the absolute value of R is strictly less than 1, then the limit as n goes to infinity of R to the n is 0. Okay. That's it. Now there's a definition associated with this. Sequences of the form a times R to the n, I should say, let me write it like this. an equals a times R to the n. These are called geometric sequences. And so what our theorem says, there's really a little bit more to it than this. But what our theorem says is that geometric sequences, and later we are going to talk about something called geometric series, which are different. So you need to get the vocabulary straight in your head. Geometric sequences converge to 0 if the absolute value of R is less than 1. So a sequence of the form, some constant times some other constant to the n, these are called geometric sequences. The number R here is called the common ratio. And the single most important thing you need to remember about these guys is that if the absolute value of R is less than 1, then the limit of the R to the n part here is 0. I want to spend some time justifying this to you, and then I'm going to give you a sort of slightly fuller result, a slightly more robust result But in order to understand that slightly more robust result, it's useful to just think about it in this way. So what's really going on here? Why? Why would something like r to the n, if I'm raising a number to bigger and bigger and bigger powers, have limit 0? We usually think that if I start raising a number like r, whatever it is, to bigger and bigger and bigger powers, then the thing gets bigger and bigger and bigger, right? Like 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32, 2 to the 6 is 64. That shit's getting big. But the common ratio there is 2, which doesn't have absolute value less than 1. So in order to show you what's going on here, I'm going to look at some graphs in Desmos, which means I'm going to need to pan away from this. So does anybody need more time to write what's written here? Let me know right away. Okay, we go into Desmos then. What I'm about to show you are some graphs. There'll be graphs of continuous functions, not graphs of sequences. And I want to focus on what's going on over here in quadrant 1. So these functions are all of the form x to the n, yeah? Yeah. And you notice something very special here happens at 1. The function x to the 6, if you look anywhere to the right of 1, is very, very big. But if you look to the left of 1, he's very, very small. In fact, he's smaller than all these other guys. So as the power gets larger and larger, take your favorite number, like 1/2. Right here, the y value on this graph is 1/2 squared. I can get it, there you go. Then the value on the blue graph is 1/2 cubed. The value on the green graph is 1/2 to the 4. The value on the purple graph is 1/2 to the 5. And the value on the black graph is 1/2 to the 6. So you notice that if you took a particular x value here and applied larger and larger powers to it, it's actually moving down rather than moving up. Functions like x to the n stretch things out if you're outside the interval -1 to 1. But if you're inside the interval -1 to 1, functions like x to the n squish things down. So that is really why this result is true. But I'm going to look at some specific examples to try and convince you, because I'm not sure that that picture is convincing enough. This is a geometric sequence. because it is some constant, in this case 1, times some other constant, 1/2 to the n. So r here, the common ratio is 1/2. Let's look at the first few terms. A0 is 1, A1 is 1/2, A2 is 1/4, A3 is 1/8, A4 is 1/16. What do you notice about these numbers? As n gets bigger and bigger, what are these numbers doing? 1, 1/2, 1/4, 1/8, 1/16. They're getting smaller and smaller and smaller. In decimal form, this is 1.00, blah, blah, blah. In decimal form, this is 0.500, blah, blah, blah. This is 0.25. This is 0.125. This is 0. I'm not so sure what 1/16 is, but it's smaller than this. These are getting smaller. Any geometric sequence where the common ratio is like 1 over something, like 1/2, 1/3, 1/4, 1/5, the calculations are going to be pretty easy. But if you have like 2/5 or something like that, those calculations get a little bit harder. It gets a little bit tougher to justify that those sequences also go to 0. The full result on geometric sequences is this. That the limit as n goes to infinity of r to the n can be broken up into a few different cases. It's equal to 0 if the absolute value of r is strictly less than 1. It's equal to 1 if r is equal to 1. That's kind of boring, right? Then you've just got the sequence 1 to the n. That's just 1, 1, 1, 1, 1. It doesn't exist if r is equal to -1. We've seen that case explicitly as well, right? The -1 to the n sequence. And it's plus or minus infinity if the absolute value of r is strictly greater than 1. Right? If r is like -5, then the sequence bounces back and forth between positive infinity and negative infinity as r goes to infinity. If r is like +5, then the sequence just runs off to positive infinity. But in either of these cases, the sequence is divergent. So the sequence an equals a times r to the n will converge provided the absolute value of r is less than 1 or r itself is exactly equal to 1. In this case, the limit as n goes to infinity of an is 0. And in this case, you're talking about a constant sequence. So the limit n goes to infinity of an here would just be the constant term a. It's really this one that's interesting. Because constant sequences are kind of boring. And we're going to use this result heavily in section 11.2 when we start developing some results on infinite series. All right. There is one more theorem on sequences. It's the monotone bounded sequences converge thing. And it's a very cool result. But unfortunately, it's not something that's super easy to use. So I'd rather give you more practice with these. There's plenty of practice with these geometric sequences in your homework. Maybe I'll do one quick problem here. Let's say, investigate the convergence of the sequence whose first few terms are given here as 2, and then let's say negative 2/3, and then positive 2/9, and then negative 2/27, and so on. So here, the first thing we need to do, this is kind of like one of those problems we looked at on Monday, where you need to look at the pattern and deduce a formula. Here, let's say, suppose n starts at 0. Yeah, very good. Maggie and Juan both got it. Here, the formula for an, a0 is 2, a1 is 2 times negative 1/3, a2 is 2 times positive 1/9, a3 is 2 times negative 1/27. And if you start looking for the pattern here, an is 2 times negative 1/3 to the n. So it's not quite 1/3 to the n because it's alternating, bouncing back and forth. So Maggie, in your formula, you could slap on a negative 1 to the n and then simplify it to this. So this is a geometric sequence. Because it's equal to some constant times some other constant to the n. A is equal to 2, and r is equal to negative 1/3. Another way to detect that the sequence is geometric is by noticing that to go from here to here, you multiply by a constant. To go from here to here, you multiply by a constant. To go from here to here, you multiply by a constant. To pass from any given term to the next term, you're multiplying by negative 1/3. That's why we call this the common ratio. Because if you divide two consecutive terms, you get the common ratio. Or to pass from one term to the next, you multiply by the common ratio. Okay, so our task was to investigate the convergence. So far, we've found a formula for an. How do we determine whether the sequence an converges or not? What should I try to do with an to figure out whether or not it converges? What's the definition of convergence for a sequence? Right, we take the limit. So now the limit as n goes to infinity of an is the limit as n goes to infinity of 2 times negative 1/3 to the n. The 2 is a constant multiple. He can pop out. And our task is to figure out the limit as n goes to infinity of -1/3 to the n. What is that limit and why? Good, that limit is 0. Why is that limit 0? Good, because the absolute value of r, do not forget the absolute values here, so important, right? That's why I chose this example with a negative r, is the absolute value of -1/3, which is +1/3, which is less than 1. So geometric sequences go to 0 if the common ratio is less than 1 in absolute value. Okay. You have a few homework problems that rely on this fact, and it's important that you remember it exactly. Remember, my suggestion is in the back of your notes, dedicate 3 pages to convergence results, 1 for integrals, 1 for sequences, and 1 for, I can't do it, 1 for series. We've now covered all but 1 of the convergence results for sequences. So after today, you should look at your notes and go back and add these important theorems to the second of those pages, the one on sequences. 1 more result. I saved this one for last because we don't actually use it very much in this class, but if you go on to take an advanced calculus class or a real analysis class, you will use it a lot there. Bounded monotone sequences converge. That's it. Now this is a loaded sentence because we don't know what bounded and monotone mean. Bounded means that the absolute value of an is less than m for all n. So this means there is a number capital M such that the absolute value of am is less than m for all n. In other words, the sequence doesn't run away to infinity, right? A bounded sequence is one whose outputs don't get huge. And monotone means always increasing or always decreasing. Right? You may have heard the term monotone in Calc 1 when you talked about increasing and decreasing functions. A function that's always increasing is called monotone increasing. A function that's always decreasing is called monotone decreasing. Mono means one, right? Mono is the Latin prefix for one. So one way, monotone, always going up or always going down. And bounded, remember, means like doesn't go, there's a ceiling that it doesn't go through, and there's a floor that it doesn't go through. Bounded means that the graph can be contained in some horizontal window. Again, this theorem, while beautiful, is not as useful for us as it would be in a slightly more abstract class. But I want to take the last few minutes of our last day here talking about sequences to try and convince you that this theorem is true. Because understanding the proof of this theorem is a useful thing for seeing how well you understand the idea of a sequence converging. So here I'm going to sketch a monotone increasing function that's bounded above by m. The fact that my sequence an is bounded means that it never gets bigger than positive m and never gets smaller than negative m. So my sequence is trapped in this window. Let's suppose that A0 is like right here. Maybe A1 is like right here. Maybe A2 is like right here. My sequence is monotone increasing. So suppose AN, the sequence AN is bounded by M and monotone increasing. Okay, well, A3 then, because I'm increasing, has to be bigger than A2. I have to keep going up. A4 has to be bigger than A3. I have to keep going up. A5 has to be bigger than A4. I have no choice but to keep going up. But oh shit, I also have to stay inside this window. Ah, fuck. Look at that. It has no choice but to pile up on the least upper bound. Since I always have to keep going up, the next dot is going to be a little bit above this one, a little bit above this one, a little bit above this one. But since I'm bounded, I can't go through this ceiling, which means all those dots have to start piling up on this ceiling. And when you look at that graph, that's the graph of a convergent sequence, isn't it? It has no choice but to converge because it's bounded above, but monotone. So I can't turn around and go down. But I also can't break through this ceiling, which means that these dots have to start piling up on that ceiling. The result of that, though, is that these dots have to all start looking like they're going towards the same value, which means that the sequence is convergent. And if you are monotone decreasing, you just turn the whole thing around. Decreasing but can't go through the floor means it has to start piling up on the floor. So every bounded monotone sequence must converge. And what's more, the limit has to be whatever the smallest upper bound is, or whatever the smallest lower bound is. This is kind of how mathematicians think, right? You like to think about what sort of characteristics a sequence could have that would force it to converge. And this turns out to be a really useful set of characteristics. If you're always increasing, but you can't go above a certain point, then you gotta converge because you have to start piling onto that ceiling. Or if you're always decreasing, but you can't go below a certain floor, then you have to start piling up on that floor. All right, thank you guys for hanging around. I know we went about 6 minutes over there. I really appreciate your patience. The only place that you actually use this theorem in the homework or on a test, I probably wouldn't put this on a test, but the only place you would use it in a setting like that is with recursive sequences. And there is, I think, one homework problem that you have which has to do with using this theorem in recursive sequences, but I made sure that it's got the little walkthrough. So it's not something that you need to stress about for the purposes of the test. Focus on all the other sequence stuff. But when you get to that problem in the homework, if you're rushing or if you're feeling pressured or if you're feeling like you're not fully understanding the rest of the problem, skip it. Skip it for now, come back to it later. But then once you do have some free time and you want to think about some cool math things, come back to it. because it is cool. But again, make sure that you're comfortable primarily with the result on geometric sequences. Make sure you understand this entirely. And make sure that you are comfortable with the renormalization trick. Those are the two most important things. You can use L'Hopital's rule again if you want to, but remember to do that, you need to swap the n's for the x's. You need to make sure that the functions there satisfy all the conditions of L'Hopital's rule from Calc 1. That is it. Now, I will be posting some videos and things like that to help introduce you to the concept of series. And I will be going out of town next week from Tuesday through Saturday. So I'm going to be pre-recording those lectures for you guys, which means, yeah, you don't have to get up at 8 a.m. if you don't want to, but make sure that you are still very disciplined about watching the lectures on Monday, Wednesday, and Friday. Monday, we will have a normal lecture. I will be here, but Wednesday and Friday, the lectures will be pre-recorded. You can watch them whenever you want. But please be disciplined about watching them and doing the homework. Treat it the same as you would anything else. Even though I'm out of town, I will be bringing my laptop. I will be doing office hours. We will be doing all the normal class things. It's the only difference is that the lectures will be pre-recorded. All right. I hope you guys have a lovely rest of your day, and I will see you Monday, if not in office hours. Take care. You too.